Hi everyone, this is the final presentation for our project implementation for CS 5800 algorithms. Me and my teammates Abhinav Nippani, Adwait Patil, Ayush Patel, and myself Shivansh Verma have implemented various clustering algorithms to understand and evaluate credit card usage with the goal of creating a robust system to identify the different demographics of user as well as fraudulent behaviors. In the contemporary era of digital banking and e-commerce, credit card fraud has emerged as a significant threat to the financial security and the stability of global financial ecosystems. This project aims to address the pressing concern by implementing and analyzing the effectiveness of four prominent clustering algorithms: DB-scan, Optic, K-means, and GMMs. The project's central question focuses on the effective implementation of these algorithms to accurately identify and mitigate fraudulent activities in credit card transactions. A key innovation in this project is the optimization of EM step within the Gaussian mixture model, optimizing clustering algorithms in k-means clustering, which is vital for refining cluster assignments and centroid updates, thus influencing the overall performance of the algorithm. Additionally, the project explores the efficacy of both breadth-first search approaches in the implementation of DB-scan, aiming to determine which method yields better performance in context of credit card fraud and detection.
Like Shivansh explained, we have implemented four different algorithms for clustering. The first one is k-means, which is a simple unsupervised method. The next one is Gaussian mixture model, which is a probabilistic approach. Third one is DB scan, which is a spatial based clustering approach. And the fourth one is optics, which is a improved version of DB scan.
Okay, thanks, Abhinav. Next, to get started with our project, the first step was doing the exploratory data analysis. On the left, you can see the graph for the correlation matrix. The blue one shows positive correlation, whereas the red one shows negative correlation. And the size of the dot is positively correlated to the strength of the correlation between two features. And this helped us to drop features which were highly correlated and didn't add any new knowledge for our machine learning models to run. And on the right, we see the purchase frequency distribution. It is the only feature which was not skewed, whereas all the other features had high skewness. And so we had to scale the data to get better results. Okay, so starting with the first algorithm that we implemented, k-means clustering. So k-mean for applying k-means clustering, we had to first pre-process the data as I explained, because the data was highly skewed and had only one good data point. In this application, we tried to optimize clustering by applying various distances to find clusters better and with optimum time complexity. K-means has a time complexity of O(n) square. We tried to get it to close to O(n) by applying different NumPy array implementations. Now, k-means is a clustering algorithm used to divide the data into k number of clusters. The algorithm operates by randomly initializing each cluster center and then iteratively updating these centers to be the average of the data points in the clusters. This process continues until a defined criterion, example, a situation where the centers do not move, is met. The elbow method and silhouette score were used as supportive means to get the best number of K or the best number of cluster centers for this algorithm. Elbow method is one of the toughest decisions for the K-means algorithm in determining how many clusters the data should be divided into. The elbow method is a common technique used for the decision. This method involves calculating the total number of cluster sum of cluster squares for different k values. As the value of k increases, WCSS decreases. However, after certain k value, this reduction amount becomes insignificant. This point is called as the elbow, which helps us to determine the optimal number of clusters that our data should have. And after implementation, we found that three was the optimal number of clusters we had for our k-means cluster. Okay. In this slide, we see two graphs. On my left, we have the elbow method versus the silhouette score. We can see that when the number of cluster is three, the silhouette score is highest, which means that it had the best clusters. Whereas if we see as the number of clusters increases, we can see the silhouette score dropping, which means the clusters are not pure enough or good enough. So three is the optimal number of clusters that we found. On the right side, we can see all the three clusters are well defined. The purple is the one which is highly prone to credit card fraud, whereas the other two are less likely. And we can see that our uh, K-means algorithm does a pretty well job of differentiating all the three clusters. Next slide.
Thanks for that. Now the second algorithm is GMM, which is a different clustering algorithm. So this assumes that the data is generated from a mixture of several Gaussian distributions, uh, and also it's basically a probabilistic method of clustering. As part of this, we have the expectation maximization step, which is employed to iteratively update the parameters. This consists of an E step and an M step. In the E step, what we do is we calculate the probability of each data point belonging to each cluster, considering the Gaussian distributions with the means, covariances, and weights. In the M step, we update the parameters, including the means, covariances, and weights of Gaussian distributions based on the above computed probabilities. And similar to the k-means approach, once again, the optimal number of clusters in GMMs can be determined using techniques such as elbow method and the silhouette score. The best time complexity for GMMs is O of n into k into d cube, where n is the number of data points, k is the number of clusters, and d is the dimension of the data set. So if you see the graph, so we can see that we have two clusters formed, and uh, the ones in sort of like yellow color. So these are the fraudulent detections, and as we can see in this plot, it's not so satisfactory. And one of the possible reason is that there are too many parameters in our particular data. So hopefully by hyperparameter tuning, we can get a better sort of like cluster formations. Okay, next slide.
We have also implemented DBSCAN, which stands for density-based spatial clustering algorithms for with noise. The algorithm works by identifying core points that have bin samples, number of neighbors that are within another parameter known as epsilon distance of the given point in consideration. Now, to calculate the distance metrics, we can use several methods such as Euclidean Manhattan, but for the sake of simplicity, we have implemented Euclidean matrix to identify the nearest neighbors. After the core points are identified, we start creating clusters of the core points that are not visited by visiting them and assigning them and their neighbors, which are also core points, as a cluster. After all points, we move to identify a non-core point and start assigning them cluster based on their proximity to another core point. This helps us to maintain the overall quality of clusters by identifying dense clusters and filter out the noise that are besides these different clusters. To implement DBSCAN, we used a queue by taking inspiration from the BFS. We are first creating neighborhoods by finding all the points that are within epsilon distance of each other. Then we run DBSCAN by using BFS to check their neighbors and assigning them the cluster labels while visiting them. So this step is continued until all the core points are visited and all the non-core points are either identified as belonging to a cluster or noise. The overall time and space complexity of our implemented approach is order of n square. Next slide. As you can see, DBSCAN does a good job of identifying a lot of noise and a lot of different clusters by itself without us explicitly telling us how many different amount of clusters we need to identify. As you can see, it has identified three clusters: yellow, red, and blue. From our understanding of the EDA done on the basis of quality of this clusters, we could claim that the yellow cluster is basically average users who are using the credit card for normal purposes. The red ones are the clusters that are below average users who do not use their credit cards to that extent. And the blue ones that are seen on top of the graphs are the most likely to commit credit card fraud or have a high running average balance. This helps us to identify the cases where we could likely see a credit card fraud being committed and thereby not increasing the credit limits or any other features. Next slide.
As Shivas mentioned, we have used DBscan, and in further analysis, we also used Optic, which is a generalized and optimized version of DBscan. So, Optic is a density-based clustering algorithm and can be used as a generalization of DBscan. However, it is known for its ability to identify structures of different densities in a dataset instead of using a single epsilon value as DBscan uses. This algorithm uses a ball tree data structure, constructing a ball tree that has a time complexity of O n log n, where n is the number of points in the dataset. The reachability of the distance is calculated for each data point. This determines how close a point is to the another point at a certain density. Based on these distances, a reachability graph is created. Valleys in the graph indicate the density-based clusters. Now, coming to the how is the space and time complexity of the algorithm. The query region runs the ball tree for neighbors, with which we can set a max epsilon value of, and this gives a time complexity of O log n for a single query. However, since this is called for each point, it is not processed yet, and the worst case time complexity will be O n log n. And next, we go to the expand cluster process. In that process, it iterates to the neighbors of each given point to expand the cluster order. In the worst case, the data points are densely packed and each point has many neighbors. This could lead to a situation where nearly every point is considered as a neighbor and thus giving a worst case time complexity of ON. In the combining these complexities, overall worst case complexity of optic implementation is ON square. Optic can perform better than ON square when the dataset has sparse distribution or when the max epsilon limits the number of points to be considered in each neighbor query. However, it is important to note that the average time complexity might be better than the worst case depending on the data distribution and the parameter settings for min sample and max epsilons. In this, we can see the graph for a normal distribution where the optic is implemented without dimensional reduction or without performing PCA. So in that we can infer that it gives more insight than DBscan. In DBscan, we can clearly see three clusters. In optic, we can see multiple clusters, while majority of them are gray, which indicates the average balance of the customers. This indicating these are neutral, and we can see no fraud committed in this users for the credit card. And when you perform dimensionality reduction, since our model would perform better and faster in spaces of time and space complexity, we can see a much more clear version of the clusters being plotted. Now we come to the conclusion of comparing all the four algorithms, and these are the results we have inferred. So on the k-means algorithm, after dropping redundant features, it gives us the best result among all the algorithms. The silhouette score and the elbow method, along with the Gaussian initialization for centroid, helps in getting these results. The performance of GMM is currently unsatisfactory, but extending the number of iterations could potentially enhance its results. It might be worthwhile to evaluate this approach for a supervised application for fine-tuning. In the DBscan approach, it gives a highly fair silhouette coefficient, indicating that this approach also defines clusters quite well. The optic performance is generally low compared to the other two methods depending on the dataset used. Particularly, this negative silhouette coefficient indicates that the clusters are poorly defined. Thank you.